Hello everyone. Today I would like to talk about stock and flow basics in our Thinking in Systems series. And we will see how quantities accumulate and move in our systems. And remember that systems is not only about computer science, but I will target, of course, more on computer science and software architecture. But you will see that we can apply this to any scenario in life, social interconnections between people, companies, politicians, agile, management, how an company is organized. There are systems everywhere. And if you start to understand how the systems work, what are the elements, what are the interconnections between them, you start to understand better how things work, and it will be easier for you, first, again, to understand them, and then to optimize or detect bottlenecks or maybe some failures that you can take advantage or maybe want to fix them depending on the context. But today I would like to talk about stock and flow basics. And by the way, I already provided an episode introducing this subject if you want to know more. Sometimes for the people that already see my videos, they know that I talk a lot and I usually review a lot from previous videos, but I'll try to be fast in this one. And again, you can see the introduction in the first episode about thinking in systems. It's called, I think, introduction in one of the videos. So what are systems made of? This is just a recap, just in one slide, what I talk about in a previous slide. I've talked more than what is written here, but this is the biggest highlight points. So we have elements like people, code, tanks, parts, servers, storage, databases, everything that somehow is related to the quantity or something, they are elements. The elements are things that we can correlate between them. If you have a boss, you have a system. The system gives you orders, which is outflow. And from your point of view, you are the inflow and you are another element. And this is a system. It's called a hierarchy in a company, and it's a system because it has a purpose. It's to manage something, and it gives you orders and you do something. So there is a purpose. So there is elements, which are the people. They are interconnections, communication pipes, calls. Maybe you receive by email. Maybe you receive by just voice. But people usually create a system. They say, okay, if you want something important, you should send me an email. So I have elements, which is these two persons, and we have this channel, which is interconnection. And you define in your system, which is to, let's say, manage important things. You have an interconnection, which is the email. Okay, then you have a purpose and a function. This is the most important part. You only have a system if there is a purpose. If you are two people waiting for the bus, there are two people, maybe they talk to each other, so I have elements, you have interconnections, but there is no system because there is no purpose on what they are talking, unless they are arranging something. But otherwise, it's just two people talking. There is no purpose or function on that connection between those two people. So these three concepts are always correlated with each other. But behind all that, behind this, there is always something that is called stocks and flows. And we'll see in a moment what they are. So this is, I think, if you understand these three, now the next step is to understand stocks and flows, because this is what influence the behavior of your system. So let's see, first define the stocks and flows. What is a stock? It's a quantity that accumulates over time. And it doesn't matter what is the subject. Can see money in your wallet, on your bank. Maybe it's messaging in a message system like Kafka or other kind of messaging systems. Water that you can have in a bottle, you can have in a cup. Maybe it's a reservoir of water. Maybe data in a database, in files that you have in a file system. If there are some quantity that can increase and decrease, you have a stock. I think it's quite easy to understand. And you have the flow. The flow, they fill or empty the stock. They put things in the stock and take from the stock. And that's it. Okay, if you have an inbox in an email, your application, it's the stock. And every time you receive a message, there is one more message. So your stock increases. And if you delete email or move to another place, to another stock, for instance, you are just decreasing the stock. So this is the relation between stock and flow. In case of the email, of course, the flow is someone send you the email, and the output, it can be moved the email to a different stock like trash or something that will be empty later. So stocks are the memory of the system because they have values. So if you you can, in points in time, let's say your measure, it's a second, you can take a snapshot of the system. At this second, I have 20 messages in my mailbox. In 60 seconds, I will only have 10 or something like that. So you have a memory and have a history. And with these values, you can, let's say, forecast things. You can understand the behavior of the other system. And the flows are the activity that fills or empties the memory or the stock in this case. So why they matter? Stocks delay change. Systems don't react instantly, meaning that when someone sends you an email, you receive the email, okay, but there is no reaction. But maybe if you start to have more than 30 or 40 messages that are unread, maybe that will change something. But since you have a stock, you can receive something and take some action later. And this can happen in any place. Maybe, for instance, during winter, maybe you are accumulating a lot of water that will only be spent on the summer. So the system will not react instantly. It's not that the water enters and it will go out instantly. Sometimes just accumulates, creates an history, and then later will be change on the system. Flows are leverage points. They influence the system behavior. That's what changed the system. If it's raining a lot, of course I will accumulate water fast than if it's not raining. Okay, understanding them help us to predict long-term outcomes. If you understand how the stocks are growing, we can forecast values. Okay, stabilize or accelerate systems. We can stabilize or accelerate. If you want to accelerate the system, I can just, for instance, reduce a stock, which means that will trigger probably faster. Imagine that I only trigger when it's full or reach specific points. Of course, there are systems that don't wait. For instance, if you have a web server and receives a request, you want to process as fast as you can and access, for instance, the database and respond. So in this case, you have an inflow, we increase one on the stock, and you try as fast as you can to reply, so it will be removed from the stock. But you can have a burst of requests and receive 100 in 2 or 3 seconds. And now imagine that your outflow is just 20. Now, in this case, it will be completely different, and maybe you want to do something about it to stabilize your system because you are receiving too many inflows and you cannot throw out, meaning using an outflow, taking from your stock that request. Okay, so I will using here computer language and not computer language so you understand this science applies to both worlds, okay? And avoid surprises. For instance, bottlenecks, which will be one. That can happen if we don't do nothing about a load balancing or something in a computer system. Examples of misunderstanding stocks. Sometimes probably we don't understand quite well the stocks and it can be an issue. For instance, imagine that you want to optimize a system based only on flow. Okay, we don't care about the stock. So increasing CPU speed without addressing request backlog. That's usually a problem. Sometimes you say, okay, we are receiving a lot of requests and okay, we just increase the CPU speed. And probably it will not be the solution. Because it's, it's like we are increasing our stock so we can handle more trades or something like that. But probably it's not the best solution. Maybe the best solution is to reduce the number of requests or prioritizing or creating some kind of a throttling concept in architecture or software design where we control who can access or how many times our system can be accessed, or maybe reduce quality, meaning that we reduce the flow, we control the flow and not the stock. It depends. The thing that it's important to understand here is the solution. It's not only about the stocks, but about the flows. We have to understand both because both influence the system. Adding more clients without scaling the session store, meaning, okay, we are saying, okay, we want to earn more money, so we'll have more customers, we'll open our application to other departments or other entities that can access our system. But we forget to... or we forgot to add the session store, meaning we are receiving 100 clients, but we can only handle 30 clients. Of course, it's not common. I'm doing these numbers, but as you know, it will not be 130. Probably it will be 1,300 or something like that, which will be more according to the current ways of developing software. But the thing here is to take some thinking about when we have to understand the stocks and the inflows, because people say, you have the stock, so I increase the stock. I put 2 servers, it will handle more information. Okay, but now you have the outflow. The database can handle all those requests. You are increasing a lot the web servers, but what happens to behind this? So there is always this relation between the inflows and the stock. Okay, how to think with stocks and flows? Okay, that's kind of a mindset that you should have to understand this. Ask what accumulates over time. That's the first thing that you should do. Where are the stocks? What accumulates here? We have requests. What will accumulate here? It's the number of threads. Okay, every time I receive a request, a thread is created to handle this request. So, and my web server wait for the next one. But maybe you have a pool of only, let's say, 50 threads. Okay, so now we have an issue. If you have more than, if we cannot answer, there will be a relation with latency. I'm trying to avoid to discuss completely the metric latency because I think it's it deserves a video per se. But let's say you receive a request and now it takes, let's say, 3 seconds to respond. But in 2 seconds you receive 60 requests, and if you can only handle 50, there will be 10 that will be waiting because the other 50 are still being processed, and only after 1 second they will be available for the other 10. But of course, now you have these 10, but maybe 60 or 70 more that arrive. So you will start to see that will be a bottleneck. By the way, the latency, it's the time that it takes for you to do a request and receive the response. And so it's not the request time. People say, okay, it took 2 seconds to request. No, probably the request goes to web server, then behind the scenes go to a database application, maybe connect to an external system, and it can take a while. Sometimes people forget to measure all these, let's say, hops or connections between the servers to understand what is the time for the latency, or at least to try to estimate it. So, by the end of the day, ask what accumulates, what is the entity, what is the stock. It's not the server, it's the number of threads. A server can have more than one stock inside. Identify inflows and outflows. This is the most important. Requests to a web server, and now there is an outflow to, let's say, a service layer or to a database that relieves. In this case, it will not be the outflow. This will be an inflow to the database. The outflow will be the HTTP response to the browser, because that's when the stock will decrease, because you do the request and now you have the response and the thread will be free for the next one. Estimate delays. Do change appear instantly? Okay, this is again what we're discussing in point 1. Consider limits. Can the stock overflow or run dry? This is most important. What is the capacity of our stock? We can handle 50 threads. That's our limit, so we have to design our system for this. Probably we have to control the inflows, maybe with throttling or other mechanisms to make sure that it doesn't overflow. Run dry will not be a problem, but maybe we want to monitor why is not our system receiving any request, or we have a really bad business, or maybe something is wrong. Maybe someone changed the IP or forget to pay for the certificate or something like that. And predict of future state. If you understand all these measures, we can predict, and it's something that we'll see in a moment. Design implications. Systems should be designed to monitor critical stocks. Of course, you want to monitorization, as you know, in software. If you look well to this, to consider all of this that we have here, to check the accumulation, if it's overflow or run dry, to identify how many requests we are receiving, how many response, what is the quantity, what is the volume, and things like that. Even the delays we want to measure in our monitoring system, and sometimes even throw some alerts. Okay, and then we can adjust flows based on the stock state. We can, for instance, if our stock is the CPU, and I work in a place that every time it was a bank, and every time a stock or a CPU reaches the 70%, we start to send some warnings. It was not an error, but we start to some warnings. Maybe we should do something, because it was not normal to reach the 70%. Maybe something was not right. And we wanted to trigger some alerts or actions when this threshold were hit. Okay, and model, of course, worst case accumulation scenarios, meaning that what if we have a stock with 50 threads, but we receive 60? What is our remediation problem here? What should we do? Just refuse? Maybe we should review our architecture. We have to model this worst case scenario and see what happens. Let's start with some examples. Let's say personal finance should be simple to understand. Our stock, of course, you have some money, can be our wallet, bank account, and things like that. And we have an inflow with some values, and the outflow, it's the expense. I think it's quite easy to understand. And you can see an example here, a visual one. We have some income, some interest. Sometimes this interest, and I will talk about it in a future video, can be a kind of a feedback, meaning that we put money here and this 1200 here can feed back with an interest, and we can receive, for instance, 20 at month. And which is quite interesting because the feedback loop will work as a kind of inflow that influence our stock. Sometimes the stock influences itself. And I can give you an example. Imagine that you have you can handle, let's say, thousands of threads. And you say, okay, I just increase the number of threads because I have more CPUs in my machine, so my stock can handle a lot of requests. The problem is if you have too many requests, too many threads, the problem is that there will be slots in threads available to handle the request. But now you have a process that should go through all the threads. And this process takes time. So you have a kind of a feedback that is, let's say, delaying, bringing some problems to your architecture, not because you don't have the correct inflow or the stock, but it's the feedback. It means that the way the stock is, the capacity of the stock is influencing itself in a bad way. Maybe sometimes it's in a good way. In our case savings account, it's a good way. But this will be the purpose of a different video called feedback loops. That happens, of course, in money, but also happens a lot in computer science. And sometimes people forget to think about it. Sometimes they think just about the straight things. I'm receiving stuff, I have a stock, and now I have an outflow. But sometimes the stock influences itself. So public health, vaccination, the same. So the stock will be the people that are immune. That's what we want to control. We want to increase the stocks amount, so we start the vaccination program. But of course, during the time that we are taking the vaccination, along the time, throughout the time, there are people that will start to lose the immunity. So it will be a balance, and we have to think careful about what can we do per day in vaccination. But at some time, we have to think that some of part of the stock here, along the time, there will be a feedback that will start to decrease by itself because of the time and not because of any inflow. Okay. Manufacturing inventory, that's quite easy to answer. We have a factory that produces 1,000 a day. We have an inflow, manufacturer, we have an inventory, things that we want to sell. And of course, this is the customers. Here, the demand is bigger than the one that you can produce, which is a good thing from the profit, but it's not good because at some time you don't have nothing to sell. So people start to worry about what happened to this company. Okay. Water reservoir system, it's the most common to present in this example. So I have water, and I like this one because you have multiple inputs and outputs, and some of them is something that sometimes we forget, which is, for instance, when we consume the water from the reservoir, there is also the sun there that consumes water, and it consumes a lot. If you put water in a terrain during the day and the sun is over it, after a few hours there is no water anymore there because it was taken by the sun. And we can receive again from the sun the same water, so we receive it here as a rainwater. It's a kind of feedback, but it's not a reservoir that's causing problems. It's an external element which is called the sun. Okay, and of course we can take water from the rain and from the river. Let's see a software example. Let's say message queue, because it's simpler to understand. Imagine that you are in a rush hour for 2 or 3 or 4 hours. Let's say for 2 hours at the morning between 8 and 10. We receive a lot of message because there is some sync mechanism or something when the companies start to work. So we have a queue with 12,000 messages at 8 hours in the morning, and the producers are sending us 500 messages, but we can only work on, let's say, 480, meaning that every second there will be an increment of 20 here, which can be a second. It can be a problem, but it can be a problem if we reach the limit of the stock, or something starts to degrade. Otherwise, if this happens only for 2 hours, maybe there isn't a problem. So let's see if that's a problem or not. So imagine that we have a chart like this, and we define that our system can handle, from the tests that we did, 50,000. And you say, okay, it's a lot, 50,000. We have 12 here. They only vint per second. It doesn't seem too much. But when you do the math, we reach the conclusion that after half an hour, approximately, you reach the point. So you start to have problems in the system. That's one of the things when we put some values on these kind of things in our inflow, outflow, the net grow, the queue size, which is the stock, and we do the math, and it's quite simple to do this math. It's just a very simple formula. We reach past that after 30 minutes, there will be an issue. So our system cannot handle all these requests. So we have capacity issues like unbounded grow, at least for 2 hours. The resource will be exhausted. Okay, there will be increased latency. After half an hour, there will be a problem. So the message tries to be inserted on the message queue, and it will be a second, at least for a while, because again, they will start to accumulate here, and it will reach the point. So for any message to enter, some of the message should go out. So there will be also a lot of delay, and the net grow will increase until it will be completely unreachable, the system here. So there will be increased latency, meaning a very waiting time from the client point of view. And of course, there is the risk of losing message. At some point, there will be timeouts, and for sure, there will be some risk of losing messages. So for the system, this is just the capacity. We are talking about the stock somehow. Now, at the system level, meaning when you look at the system, so the application responsiveness may degrade. Of course, it's easy to understand. Back pressure could affect upstream streams, meaning that if our customers that are sending our messages also receive this message from other systems, so our customer will start to have problems, and then this problem will cascade to the sources of them. So that will be an issue that sometimes we don't think about it, but it can happen, and it can affect even the business. So possible cascading failures if you reach hardware limits. Customer experience if there is a website or something potential affected by delays or even problems. So recommended solutions, just a set of them that can be an approach. It's not an exhaustive list, not a magic points, but I think it should be enough for us to understand an approach that you can do. First, scale, meaning we can increase the stock, increase capacity to match or exceed inflow rate, meaning that's okay, I have 12 here. Okay, maybe I create another message queue, or maybe I somehow can increment the resource on this one. And you can do this, for instance, in Kafka and other systems, it's possible. So it is if you are thinking about using message queues, and if you do this math behind it, maybe say, can I scale it later? If I increase my inflow, okay, how can I do it? Okay, I can do it, for instance, horizontally, adding more processing nodes, like for more message queues, for instance, to processing these, or maybe just nodes if you're using Kafka. Load shedding, meaning implement peak traffic handling strategies. You can say, for instance, do some, I will merge with this one, flow control, and you can, for instance, consider throttling incoming message. That's one way to handle traffic. For instance, you can say, okay, each consumer in these hours, I can only accept 3 messages for them. And you agree with them about this. And they have to send you messages using this rate. You can do this. I think it is implemented. I don't know about this time, but I heard when the Netflix architect that sometimes this happens. If the people that pay more, they will have more, let's say, streaming power and streaming quality. And they can access faster than the others, some services. If you are paying less, of course, you will have a reduced number of message. Of course, it's not message, it's streaming movies, but you understand the concept. That's one way to reduce without changing your system, which is quite nice because you don't have to spend money to control your system or a big flow or inflow on your system. Sometimes it's the best approach because if you scale too much, you are spending a lot of money and maybe the scaling doesn't follow the profit. So this is an area called FinOps, if you are using cloud, but it's quite easy to understand. Sometimes having a big system and accepting every customer, maybe it's not the way. It makes you lose money rather than for you to receive money. So accept message by token. By token, it means that you can have it depends on the implementation, but imagine that you only have 100 tokens. So you can only send a message after you take a token. And if I have a token to provide you, great. If you not, you have to wait. So you don't send the message unless you have the token. So I'm not putting the burden on my system, but I'm moving this burden to the customer. Say, okay, you want to access, you have to have this. If you don't have this, don't send, because I will not accept your request. I'll just refuse your request quite fast, so my system will not be overloaded. And adapt the receiving rate by available resource. You can do a kind of a scale, intelligent scaling. You can say, okay, I receive everything, but if my the number of threads is reaching 90% of the stock capacity or the CPU, I will start to make active this kind of scenarios, like accept message by token or only allow few message or something like that. Rather than putting at the start all these rules, you can, let's say, introduce them like a kind of a feature toggles in runtime to control the behavior of the system. And another thing is establish priority message. It's the same concept that I explained using Netflix. It's the same. So people, you pay more, you have a priority. The other ones will refuse, or they should wait, or even send to a different stock, to a different server. Sometimes that's what happens. Okay, monitoring recommendations, monitorization. It's this kind of implementations. Of course, they need monitoring. So set alerts for queue depth thresholds. 90% that or the capacity you want to receive some notification, the rate of the growing on the queue, how much time it takes to receive the message and for this message to be delivered. It's important. It's not about how many messages you receive and how many of these messages are you delivering. It's these messages in particular with the ID1, how much time it takes to be received and respond to the client said, it's okay, I processed your message. It's quite important. And measure resource utilization for sure. So next steps, determine acceptable queue size, implement short-term capacity increase, something that we talk about, and develop auto-scaling solution for long-term stability. Of course, be careful in the FinOps if this is a good solution. No? Auto-scaling in the cloud, it's quite nice because you don't care. But the billing at the end of the month, maybe you should care about it. Okay, and my experience working in clouds and several of them, it starts nicely when we are developing and testing, but when it's go to production, you have to start to have a lot of requests. Maybe start to think if it was a good idea to go full cloud or not, or if you want really auto-scaling, or you prefer just to say, okay, I only accept 1,000 requests and that's it. If there is need for more, okay, not on this version, maybe later, or we will start to implement this kind of throttling, different payment systems, things like that, to make sure that I have profit. Otherwise, why bore it, right? And create load testing scenarios to validate fixes, of course. Let's say another example. Let's say we have a browser request and the database. So we have two stocks here. One is HTTP request queue. It's not messages anymore. It's HTTP requests. And there will be a thread. Let's say we have 800 here, and this browser, there are 120 requests per second. It seems too much, but it's not. If you are designing something like ChatGPT or things like that, maybe they have more than this, or Google search and things like that. So there will be a threads here. They are dequeued and sent to an application server. The application, the business logic and the application server can handle 100 here, but we are receiving more than that. So there will be a kind of bottleneck here. And then we can write database. It can also have here, but this one can process, it already has 2.5 million rows. And every time there is a write from this one, it can receive 100 rows. Of course, this is per second. It's what can be done in 1 second. So there can be problems or not. These stocks can rise, increment. This one will for sure rise. This one only accepts 100 here. So this stock will rise a lot. This one will not, because every time it receives, we can write our database, or receive the reply and send back to this one. Okay, this one will have issues for sure. So because again, it has the net will grow 20. Again, okay, I simplified both examples so it will be easy to understand. So system behavior, request queue growing at 20 requests per second, send rows per second, so there will be 6,000 per minute rows. Request queue reach 400 requests in 2.7 hours. So our system can handle this flow continuously for 2.7 hours, and database growth is steady but not immediately critical. Okay, so this is the same concept. Remember, always try to design something like this. What is the capacity for a request queue, and what is the capacity for a database? This is 3 million. It's not that sometimes database, the problem is not the storage. It's tables when they start to have big volume, maybe we have to think about, because if we think about changing these tables or something later, at some point, if you have too many million rows, it can take hours or days just to restructure the table. And I remember that work in a bank, every time there was a new column, we processed it maybe 2 days before the production to make sure that the column will be on the specific table, because there were a lot of millions and millions of tables, and yeah, it's hard to be a DBA. Let's say that like that. But the concept here is to follow the same. So always have understand these inflows, the outflows, and the stock, and do some math so you understand which one will increase at which rate, and you can at some point start to find this intersection. This one, it's for database. We don't expect big problems on the database, but we expect, for instance, on the capacity analysis for our web server. So our request queue, it's the same issues that we saw in our previous video. The queue, because there is a queue, it's not a message queue, but it's a queue of threads that there will be requests waiting at least 20 every second at some point to be processed. So there will be a bottleneck, of course, current processing capacity, because our server can handle 100, but it's receiving 120, and there will be a degradation on the system, and you will start to receive those HTTP errors saying, okay, the system is not responding, some timeouts, and so on. So queue will reach critical levels before database. So database will never have problems if you look into here, because this one will have problems before the application reach the limit. That's something that we can understand by these two stocks. This stock here, this stock. At the end of the day, we have 3 stocks. We have this one, and this one here. And this will never have a problem, neither this one, because the number of the ones that he accepts is in sync with the database. But this one, when we design it, we didn't think about how many requests could this one receive when we are full here. So database growth projection, there will be after 1 week, 63 million rows. This is a very important math to do. So, and we can talk with DBAs to say, what do you think about this? Maybe we should change our model. Sometimes maybe we should change to a different database. Once I tried to work with database with these many rows, and it will be a big problem when you want to, let's say, delete, let's say 1,000 or 2,000 of them that were spread all over this, even with index, which will be somehow slow. System impacts, short-term request and queue saturation will affect user experience. Of course, there will be no response on the web server. Database size will increase storage requirements, so it's a medium term, because remember that the request queue will reach the capacity before the database. So database is not an issue. Long-term, both systems require capacity planning. In long term, we have to think, because both will have issues in the future, but this one will have before this one. Business impact, potential service degradation, increased latency, and of course reduce the traffic, reduce trust on your system. You don't like to go to a store that blocks your request. You don't put your money there, not even unless your credit card. Okay, recommended solutions request increase processing capacity by at least 20%, so you can take a decision, maybe just a CPU that you need there, and it's not too much expensive, depending. Implement load balancing across multiple processes. Be careful of this. Increasing the load balancing, meaning just looking at here, maybe you want to increase here, but of course now you have to analyze the connection to the database. Okay, consider request throttling again during peak periods. Again, you can just decide and say, okay, I don't accept all the requests unless there are important ones, or depending on your throttling strategy. Okay, database implement data archiving strategy, so you can clean and you don't reach 60 million. Maybe you just need the latest 10 million. The other ones is information that you will never return, or when you return it's just auditing or something that can be in a different table. Maybe you implement a data archiving strategy. Monitor query performance. Of course, if the number of rows start to grow in a table, probably the performance will have a big impact. And today, the database is receiving 100 rows, but if you do a lot of inserts, maybe you start to receive only 1980, and if you don't monitor that, it will start to have problems here on this one, and of course this one was already with problems. So you understand now the back cascading issues when the stock has some problems. And consider sharding for horizontal scaling, meaning that you can, let's say, split the information by a specific table by zone or other keys. Sharding is when you split your vertical table in horizontal, let's say, subsets of data. Okay, something like that. I don't want to enter on these details. I will create videos about architecture and these kind of concepts. But for now, think at sharding as splitting your data in specific things that you understand, like zone, day of the week, depending on the business, of course. So implementation priority, immediate address request queue, because it's the one that first, it's the stock that will reach the full capacity first. At the short term, implement monitoring and alerting. Medium term, develop database group management systems like archiving and things like that, and design scalable architecture for both systems. Probably if you are going to load balancing, maybe you have we increase the number of requests that you can receive, but probably since the server here receives less, maybe you want 2 of these in front, but you want 3 app servers behind, and make sure that the database can handle this information. If you are implementing sharding, maybe it will be always faster. You will have an increase on the writes, and on the read if it's necessary, but you have to think careful about it. So that will be a priority. Of course, monitoring recommendation, set alerts for queue depth thresholds, more than 2,000 requests, track request processing times, monitor database size, again, create a dashboard. This is really useful. You have a lot of good things for metrics like Prometheus and other kind of systems that can help you in this case for software example. Next steps, increase requesting processing, implement request queue auto-scaling or not, depending again on the money, develop database rotation policy or archiving policy, design system architecture review to address growth. This is something that if you are working in a big company, probably already have one architect or multiple architects. That's once in a while they review the architecture and check based on metrics if there is something that should be done or not. But that's just good practice about architecture. So in summary, stocks are memory, they retain history, and they really influence our system. Flows change them, often influenced by decisions or delays. Know both to understand dynamic systems. Reflection exercise, if you want to practice this, pick a system you're part of, maybe in your company or maybe at your home, maybe your money finances, personal finances, maybe investments that you're doing, maybe your vehicle, like the maintenance of it. Identify at least one stock and list inflows and outflows. Ask what happens if inflow increases or outflow stops. This is quite nice. It's like, imagine that you are in a company and decide that your stock, it's the number of people in your team. What happens if you add 10 more people? How will be the meetings? Can you handle it? The meeting will have the same time. Do you understand what I'm saying? That's the kind of exercise, and this is a system. If you have agile, you have a meeting, let's say, with 10 people. Now we have 20 people. It will work. It's like a web server. Can you handle conversations with 20 people? Or you start to think, maybe I should split this. Maybe I should create a kind of a load balancer, putting one team of 10 and another team of 10 to handle this. Otherwise, it'll start to be a problem in capacity in the communication. So I'll receive a lot of messages for the team, but the team takes a lot of time to process them and take a decision. So the outflow, it will have a different rate from the inflow. It can be a problem, for instance, in Agile. So, and the question is, where's the leverage? So, thank you. This is the video about stocks and inflows. It took more than was expected, almost 40 minutes. I talked a lot, but it was a big one. I will try to the next video. Usually I try to target 20 minutes for each video because 40 minutes, it's too much, I think, to hear, and it's not programming, it's just talking about stuff. But I want to make sure that stocks and inflows were well understood, but I will try as much as possible to reduce to 20 minutes, maybe sometimes split some subjects in smaller quantities. But this one, I really wanted to spend time on it and make sure that you understand with examples what are the inflows, what are the stocks when they are applied in computer and no computer areas. And I hope it was clear enough. So thank you for watching. If you watch until the end, I know it's almost 40 minutes, and but I hope you learned something from it, and I hope that you start to see now the computer systems and even your social interactions in your business or outside your business differently, and start to understand what are the stocks, where are the inflows, how is this changing, what happens if the inflows increase. I start to have more friends, maybe I have to take more calls, maybe I have to arrange time to talk with all of them, maybe I start to choose people that I want to be with or not, things like that. It seems strange to think about this, but if you think for a while, everything that exists in our society, in our world, is always a system, at least with inflows and stocks. So thanks for watching. I hope to see you in my next videos.